Okay, in today's lecture we're going to be talking about the Helmholtz equation. The Helmholtz equation is a special form of the wave equation. It's the type of the wave equation we have when we deal with time harmonic fields. We're going to take a look at the Helmholtz equation, and we're actually going to spend the rest of the semester looking at the Helmholtz equation. But today we're also going to look at the uniform plane waves, which are one of the most fundamental solutions to the Helmholtz equation. Our objectives today is, first of all, we want to know how the time harmonic Maxwell's equations are related to the general Maxwell's equations. And specifically, we're going to be looking at source-free simple media. You need to be able to apply these time harmonic Maxwell's equations to solve problems for the rest of the semester, because we're going to use it for plane waves, we're going to use it for waveguides, we're going to use it for antennas. We want to understand the Helmholtz equation and how it's related to the wave equation. You need to be able to see where this derivation comes from. But most importantly, we're going to develop the uniform plane wave solution to the Helmholtz equation, and this you need to be able to use it thoroughly throughout the rest of this term to understand and analyze plane wave propagation problems, reflection, refraction, and other things we're going to talk about over the coming lectures. So in the majority of problems that are of interest to us, we don't need to worry about the full time-dependent behavior of our solution, right? We can encapsulate the transient behavior of our solution as the real part of a complex vector phasor. So this E is complex. Okay? And the time dependence is captured in here in this E of j omega t. So if this is some complex vector, it's got a direction and it's got an amplitude, some amplitude in phase phi. When I take this real part, I'm going to end up with cosine of omega t plus phi. Okay? And if E is completely real, then I'm just going to have cosine of omega t. If E has a phase of 90 degrees, I'm going to have sine of omega t. And we're very comfortable using these phasors because we use them throughout circuit theory. So we're going to be treating problems that have only a single frequency involved in their solutions. This isn't always the case, though. Sometimes we have problems that have more complicated time distributions, and in order to solve those, the method we use is we take the Fourier transform, and then we solve each frequency in the Fourier transform and be able to go back and forth between the two. So if my time-dependent behavior looks like e to j omega t or cosine omega t, or even, but more specifically e to j omega t, every time I see a time derivative in Maxwell's equations, it gets replaced by a j omega when I'm working in the time harmonic form. Right? So that means I'm going to multiply by the frequency and I multiply by the complex number j, which adds a 90-degree phase shift. Where does that come from? Well, if I have cosine, right, if my electric field is proportional to cosine and I take its derivative, I get the derivative of cosine as minus sine. So that's the 90-degree phase shift that comes in from this j. So when we started with we can write down our Maxwell's equations, del dot D equals rho, del dot B equals 0. These two equations are unchanged. Okay? But we originally had in Faraday's law that del cross E was equal to minus dB dt. Right? Well, the dB dt becomes minus j omega b. And del cross H was j plus dd dt. And it becomes j omega d. And when we're dealing with simple media, that is media that are linear, isotropic, and homogeneous. So linear means that D is proportional to E and H is proportional to B. Okay. Isotropic, remember, means that D and B are parallel, B and H are parallel, and homogeneous means that epsilon and mu are constants in space, although we can have boundaries between media. My Maxwell's equations, my time harmonic Maxwell's equations, I can write down for just the electric and the magnetic field intensities, and I have this form. Right? The thing to keep in mind is that this form of Maxwell's equations has several assumptions built into it. First of all, I've assumed time harmonic. Second of all, I've assumed that I have simple media. If I don't have those two cases, I need to take a step back and deal with the more general form of Maxwell's equations. We also had the equation of continuity in previous lectures, and the equation of continuity, which was del dot j plus d rho dt equals 0, can be written this way when I'm dealing with time harmonic fields. In the previous lecture, we took Maxwell's equations and we reduced Maxwell's equations down to a wave equation. And the source-free wave equation was written this way, we have here on the screen. We have now two time derivatives, and when I have those two time derivatives, I should expect to see j omega quantity squared. Right? Well, my Helmholtz equation, or my time-harmonic wave equation, is del squared of E, where now you'll notice that I've dropped this script notation, and now I've written the del squared of the complex vector phasor, right, plus omega squared mu epsilon E equals 0. And we can substitute in beta for omega times the square root of mu epsilon, or omega squared mu epsilon becomes beta squared. And this assumes that the material is lossless. We are going to talk about materials with loss in lecture 6a, but for the purpose of today's lecture, we're going to deal with just lossless media. Beta is the phase constant. It's a parameter of the material, omega times the square root of mu epsilon. It also happens to be equal to 2 pi over lambda, and is the phase constant for the medium at this particular frequency. We're going to see beta throughout the rest of the semester, so we can use beta to describe plane waves, we can use beta to describe waveguide modes, we can use beta to describe fiber optic cables, so on and so forth. Now, I don't want to dwell too long on this vector operation. The del squared operator when operating on a vector is complicated. It's a complicated second order vector partial differential. But in Cartesian coordinates it simplifies. And in Cartesian coordinates we can write down this vector wave equation, this vector Helmholtz equation can actually become 3 scalar Helmholtz equations. And do you want to remember one thing I didn't emphasize, we are working in source-free case, so we're assuming that there are no sources in this particular region of space. The sources are somewhere else. Right? So I've got to have sources somewhere. I have to have currents and charges somewhere. But in the particular region of space that I'm analyzing, we're going to assume that it's source-free. Okay? And so this set of equations is the set that I'm going to need to solve when I'm dealing with the Helmholtz equation. There are countless solutions to the Helmholtz equation. We're going to look at several of them this semester. We're going to look at uniform plane waves. We're going to look at TEM modes on transmission lines. We are going to look at TE and TM modes on waveguides. We're going to look at spherical waves in the context of antennas. There are literally a limitless number of solutions to the Helmholtz equation. And what electromagnetic theory is about is trying to determine the particular types of solutions that go with particular types of boundary conditions and sources. And so a lot of electromagnetics ends up postulating a solution and seeing under what conditions it satisfies things. So let's take a look as a first example at a solution that has this particular form. We're going to assume that that electric field phasor, it has an amplitude, and this is complex, so this is an amplitude and a phase, but it depends only on one spatial coordinate z, and it only has one component, that is the x component. And so my electric field is pointing in one direction, let's call that the x direction, and it's only varying as a function of z. And there's no variation at all as a function of y. So when I take this expression and I stick it into my Helmholtz equation, I get reduced down to this simple scalar wave equation. Second derivative of e sub x with respect to z plus omega squared mu epsilon e sub x equals 0. Or I can substitute in beta squared, and I end up with this equation here, which is one that you should be extremely familiar with. We know it has two solutions, sine and cosine. In our case, it's more convenient to use the two complex exponential solutions. And the two solutions that we're going to use are e to the minus j beta z, and we're going to label that e plus because it turns out that that's a positive propagating solution, and e to the plus j beta z, which we're going to label with e to the minus because that's a negative propagating solution. I realize that that's a little bit confusing, and this is the notation that I'm going to use. Just have to remember we have e to the minus j beta z, and you can demonstrate to yourself why this is the forward propagating solution, because when I multiply by e to the j omega t, and I take the real part, I end up with cosine of omega t minus beta z. And we know, we've seen it already in the transmission line section, that that is a wave which is propagating in the plus z direction. As t increases, z has to increase in order for a particular point on the wave to stay the same. Once we've got a solution for the electric field, we can compute the magnetic field by going back into Maxwell's equations. Remember, what we have here is a second-order differential equation. We know it's got solutions. In our particular case, we had a coupled set of equations, so we solve for E, and then we back substitute into Maxwell's equations to give us H. Let's see here. I can write out this curl in all of its glory, and when I write out the curl, okay, we can see that, well, this term is going to go away because I have no E sub z, I have no E sub y, I have no E sub z, I have no E sub y. Nothing varies as a function of y, so that term goes away, and the only term I'm left with is here. Equivalently, I've only got this component. So my magnetic field for this solution is given this way. If I assume that I have only my forward propagating wave, then I've got minus 1 over j omega mu, y hat, and then the derivative with respect to z of this quantity. Okay. When I take this derivative, I'm going to bring down a minus j beta. Right? So I take this derivative. That's a constant, so it comes out. Right? That comes out. And take the derivative of e to the minus j beta z. That's straightforward. And I'm left with minus j beta, which I'm going to write as omega squared mu epsilon, times e plus e to the minus j beta z. Of course, the omega is going to cancel. This square root of mu is going to cancel, and I have a square root of mu in the denominator. And I can write that as the square root of epsilon over mu. And I'm going to capture this quantity as eta. Right, so this quantity eta, which is the square root of mu over epsilon, it's given in units of ohms. I should denote these as having units. So mu over epsilon has units of ohms, and we call that the wave impedance of the material. And it tells us something about the relationship between the electric field and the magnetic field. In fact, it tells us about the ratio of the electric field to the magnetic field. Because if I take the magnitude of E over the magnitude of H, okay, it's going to give me E plus over eta. That's going to be equal to eta. And that's just like the ratio of a voltage to a current. It's going to give me an impedance. So what we have now is a full electromagnetic solution that satisfies the Helmholtz equations. It's got an electric field shown here in blue and a magnetic field shown here in red. In this particular case, the electric field is in the x direction, the magnetic field is in the y direction. The direction of propagation turns out to be in the plus z direction. That's denoted here, and we see things are going along. If every lambda, right, so every wavelength, the field repeats itself, and it's going to oscillate in between. And my solutions take this form. This is for the forward propagating wave. I could also have a negative propagating wave, and that's a problem you're going to do in your tutorials for this section, so you'll do the solution for the negative propagating wave. And I can have both waves present at the same time. I can have a forward propagating wave and a minus propagating wave, and they're going to interact with each other. We'll talk about interference in the next lecture when I've got waves propagating in both directions. Now, we did the derivation for an x-polarized plane wave propagating in the z direction, but there's nothing special about x-polarization. It could very well have been polarized in the y direction, and it could have been propagating in an arbitrary direction. So in general, I've got a solution that has this form, where I've got a vector, E naught, and I've got this beta vector. This beta vector we call the wave vector, and for lossless materials, it's given by omega squared root mu epsilon times a unit vector that's pointing in the direction of propagation, and that unit vector has three components, an x component, a y component, and a z component. In the problem we worked so far, beta sub x was 0, beta sub y was 0, and beta sub z was equal to omega squared root mu epsilon. But I can have a problem, say, where the wave is propagating obliquely, and maybe I've got a cosine sine relationship between beta x and beta y, and you've got that in one of your tutorial problems. So you can demonstrate, and actually this is tutorial problem number 2, that the orientation of this vector must be orthogonal to the wave vector. And the orientation is going to describe the polarization of the wave, and we'll talk about polarization in detail in Lecture 7a. So as I change my direction of propagation, my electric field and my magnetic field have to rotate as I change my direction of propagation so that I maintain the same relationship. And then after I do that rotation, I can find out that my electric field and my magnetic field form a right-handed triple. And this is going to be tutorial problem number 3. I actually inserted another problem into your tutorial. So this is problem number 3. And in all 3 instances, I've got my, and here on the picture, I've got E cross into H, gives me the direction of propagation going to the side. Right? This is what we call a transverse electromagnetic wave, meaning both the electric and the magnetic field are perpendicular to the direction of propagation. A little bit later on in the course, when we talk about waveguides, we'll have transverse electric or transverse magnetic waves that are not both transverse electromagnetic. So that brings us to an end of this lecture. The tutorial is going to test you on several things. We're going to talk about how the orientation is related to the direction of propagation, like we just saw on the previous slide. We're going to try to figure out the direction of propagation from particular problems, and we're going to look at the relationship between the electric field and the magnetic field. The problem that I inserted, tutorial problem number 1, is doing the solution for the wave that's propagating in the -z direction.